I guess it says it is. All right. All right. There is a big disadvantage to a refracting telescope. Let's talk about that. Lenses have many disadvantages in large telescopes. Large lenses are, first of all, extremely expensive to fabricate or to make. A large lens will sag in the center since it can only be supported on the edges. Right? If you've got a lens, lenses have kind of this shape right here. You can't support the middle because that's where the light's coming in, so you can only support it on the edges, and those are very sharp and it's easy to break. This dispersion causes the image to have colored fringes. I'm going to talk about that in a second with a picture. And many lens materials absorb the short wavelength of light. So some of the light gets absorbed and taken out, and so you can't see things. All right, here's kind of the problem with refracting telescopes. I would have sketched this picture right here. You know, I'm a little worried about the number of pages that I gave you for this, so you might need more than 2 pages. So you might need to add somewhere else on this as I look at this. All right, as the white light comes in, it turns out actually this is over-exaggerated, but the blue light will focus here, okay, and the red light will focus further back. And if they're all focusing at a little different place, then where do you sort of look at it? All right, where do you put, you know, if you want an image, you could actually put like a, what do you call it, just a piece of paper right here, or maybe even photographic film, and you could take the picture of it, but then you're going to miss out on the blue. The blue would then, if this is where I'm going to take the picture, it'll be very crisp for the green color, but for the blue color or purple or whatever, it's going to be blurry, and the reds will be blurry. And so because a lens has limits, because different colors of light travel through the lens at different speeds, if you have a really big lens, then you always kind of get a blurry image. And you don't like blurry images, do you? All right? So you want a blurry image. Okay, and you kind of see, here's the picture of the light. And notice how each color of light, the red, bends the least, see, as it goes through the light, and the purple bends the most. And that causes the focal point to be at a different spot. So, what's the solution to that? Well, instead of having a refracting telescope, we can have a reflecting telescope. Now, reflecting telescope uses a mirror. And you can make big mirrors. I mean, big mirrors. How big? I mean, really, really big mirrors. Okay? They are almost exclusively used by astronomers today. All right, for example, there's this one called the Twin Keck telescope, located at 14,000 feet in Hawaii, has a 10-meter collector. 10 meter, that's 30-foot mirror. And light is focused in front of the mirror. All right, we'll show a picture of that. Okay, actually, here's the picture. Here is a reflecting telescope. The light comes in here, hits the mirror. Notice the mirror is a curve, right, a little curve. And then the light then gets focused onto another mirror, and then it comes down here, and then you do have an eyepiece, so there's a lens right there, and then boom, you can see it this way. Okay? So that is called how reflecting telescopes works. So you have a secondary mirror, may be used. Notice I have a secondary mirror right here, and the primary mirror. The primary, well, that's right, you can see primary or diagonal mirror. This is also called the secondary mirror. Okay? So multi-mirror instruments and extremely thin mirrors are 2 modern approaches to dealing with the large pieces of glass in the telescope system. Of course, they're glass, they can break, so they're very, very fragile, and it's tough. How thick do you make the mirror? The science of making a telescope, a really, really big telescope, is very complex, and it's very cool as they figure out how to do it. Okay, so you can kind of see the picture again here. See how the light comes through here, hits this, and boom, hits that second mirror, and then back out to the eye of the person. Now there's a couple styles of reflectors, and the one we just saw here that has this kind of a mirror. Another one would be a little different, is the light comes, hits the mirror, and then you've got another here, and then another mirror in the middle, and it backs up to the eyepiece lens. The only problem with this, I bet you can probably figure this out, what's the problem, is that the light that comes through here, you're not going to be able to see. So, well, that's true here too. So there's always sort of a dead spot in a reflecting telescope. And so the solution to that is just to point the telescope just a little bit the other direction, and then you can see the part that you missed. All right. All right, we're almost done here. There's something called the resolving power. The resolving power is this ability of the telescope to discern detail. What do you mean by detail? All right. Resolving power is limited by the wave nature of light called diffraction. You see, here's a wave. All right. You see a wave, this wave coming through this substance right here. And actually, let's change the color of the pen here. Let's go to white. Okay. So we can see these are waves of water. As the waves hit a little opening, this opening would be, in our case, the opening to the telescope, the light makes a pattern here, doesn't it? All right, but this diffraction limits, and it causes it hard to see the detail of what you're seeing. An enlarged image that's blurry is still just a blurry image, and so we want to make it so it's a sharper image. Okay, so the problem is these waves diffract as they pass through the narrow openings. Okay, and the diffraction point source appears as a point surrounded by rings of light. This is the problem, the diffraction. So this is essentially a blurry image of a star with a telescope, and it's not good. We want to get rid of that. The way to do that is hard. All right. Now we can actually let's skip this section. This isn't important. Okay. So we can determine. So that's just a problem, is the diffraction. I should just say this. There's actually a way we solve this with something called an interferometer, and what they do is they make the telescope really, really, really big, the opening. And actually the way they do this is they'll take the telescopes and they take the telescopes and move them very, very far apart, as in hundreds of feet apart. And actually they have telescopes with mirrors that are a long, long ways away. Actually, I think I might have a slide on that. Yeah, here it is. On this particular picture, this is called an interferometer, and in this here we have a telescope, and then we have a telescope that's 3 telescopes, and even though we don't have like one big mirror because that's too hard to make, they can kind of pick all the light up and we put them further apart. So that's how we can solve the problem of diffraction. All right. Lastly, let's talk about the light gathering power of telescopes. We actually talked about this briefly, but I want to talk about it in a little bit more detail. You're going to do some problems in your homework like this. The light gathering power is LG of a telescope A and versus B, and it's related to the diameter of A over the diameter of B squared. All right, so let's figure out how this works. So let's do an example. So, of course, what is it now time? Oh, that's right, it's time for your calculator. Everybody get your calculator out. All right, so we have a light gathering power of a telescope. So suppose we have a 6-centimeter telescope and a 32-centimeter telescope. How much more light will the larger telescope gather? Now, if we look at our equation from the previous thing, is the light gathering of A, so it's LGA, I'm going to write the equation, over LGB is equal to the diameter of A, I'll just say D of A, divided by D of B, actually overall squared. So, what is the diameter of our A? We'll call A will be the larger telescope, right, 32. So I'll say 32 divided by 6, right, squared. So how do I do that? I'm just going to do it just like I have it, right? I'm going to put parentheses, and I'm going to say 32 divided by 6, parentheses, squared. So this is equal to 28.4. And then there's no units on that times. That means you can get 20 on a 32-centimeter telescope. You can get 28.4 times more light than you can with a 6-centimeter telescope, which is simple. It's just 32 divided by 6 squared. So the math on this is relatively, well, it's easy. Just understand the little equation. So the equation, of course, which is right here, that you'll want to use. All right. I believe that's the end of this podcast. The interferometers. Actually, let me talk about the interferometers real briefly. This is the thing is this is the resolution issue we were talking about earlier. This is what the image looks like with a machine that has a poor resolution. But then when you look at it with a better resolution, it's all blurry. Notice this is the blurry one. But if you use the interferometer real far apart, notice now we can actually see that this is actually 2 stars. So this picture right here on the bottom and the picture on the top are of the same thing. This one says there's 2 stars. This one you would think there was 1 star, but because we have a better resolving telescope, we're able to determine that there's 2 stars there. So resolving power is an important thing.